In this tutorial, we're going to work some of the questions in your midterm exam review that seem to be giving us a little bit of trouble. The first one we're going to start with is number 4 on page 3, which is a graph of velocity versus time. The first question is just, what is the initial velocity? When you're given the velocity versus time graph, so that's simply the y-intercept of the graph. The second part is, what is the acceleration at t equals 3 seconds? All that's asking you to do is figure out the acceleration at the the segment that passes through 3 seconds. You're not actually going to use the 3 seconds. So simply select the first and last point and figure out the slope of the line. So the first point is 2, the last point is -2, so do final minus initial, which is -2 minus 2, over the time interval, which is 2 seconds, from 2 seconds to 4 seconds. Don't use the 3 seconds anywhere. That just tells you which part of the line you're actually going to use. So when you do that, you get -4 over 2, which is -2, and your acceleration unit is meters per second squared. Part C, what is the acceleration at t equals 5 seconds? Well, the graph is flat, so your acceleration will be 0. Part D, what is the acceleration at 10 seconds? Again, just find the slope. You would get 0.5 meters per second squared when you do that. Don't use the 10 seconds anywhere. Your time change is 6 seconds. Part E wants you to tell what times the object is at rest. The object's at rest when the velocity is 0. Don't confuse that question with the same question on a position time graph. Make sure you know what kind of graph you're looking at. So when you're taking your test, be sure to highlight or underline the actual axes. If this was a position time graph, then the object's at rest when it's flat. Because it's velocity versus time graph, the object's at rest when the velocity is crossing 0, which occurs at 3 seconds and 10 seconds. Last question, question F. How far from the starting position is it after 2 seconds? First, you got to realize the velocity is constant. So I can use the v equals delta x over delta t, or the x equals vt plus x0 equation. So substitute in your velocity, which is 2, get that from the graph, 2 seconds, and you get 4 meters. Next, let's look at an example of a forces problem. So on page 7, let's look at question number 3. We've got a situation where a girl is pulling a friction block at a constant speed of 2 meters per second. The first thing it asks you to do is draw a free body diagram of the object. So there's our free body diagram. We've got gravity pulling it down, normal force pushing it up, friction's pulling it back, and Marcy's pulling it forwards with a sensor. So I'm just going to call that force Fs. And ask you, what is the net force on the block? Well, since it's moving at a constant speed, we know that the net force is going to be 0. Anytime you see the words constant speed or constant velocity or at rest, you know that the net force is going to be 0. It's very important to remember. Part B says figure out the force of friction on the block. Well, since we know how big the force going forward is, 28 newtons, and I know that the forces are balanced, then I know that the force of friction has to be 28 newtons as well. So since the net force is 0, those forces are balanced, so the rights and the lefts have to be equal to each other. Part C says now we're going to pull it harder, and we want to figure out the acceleration of the block. The thing to remember here is that pulling harder does not change the force of friction. So your frictional force is still 28 newtons. Now the forward force is 38 newtons. So I'm not just going to take the 38 and divide by the mass to get my acceleration, or the 28. I first have to figure out what the net force is. So I need to subtract the rights minus the lefts. And when you do that, 38 minus 28 gives you 10 newtons. Lastly, we can figure out the acceleration by using Newton's second law. So since acceleration is net force over mass, just take my 10 newtons, divided by the mass of 3.5 kilograms, and that would give me 2.9 meters per second squared. Part D, kind of just the opposite. Figure out how hard she has to pull to accelerate the block at 4.5 meters per second squared. So we're going to do roughly the same thing, only in reverse. Start out by calculating my net force, this time by using Newton's second law. And you get 15.75 newtons, 3.5 kilograms times 4.5 meters per second squared. Now I can use the same net force equation, the sensor force minus friction. I know how big the net is, 15.75. And I know how big friction is, 28. And so that gives me the sensor force to be 43.75 newtons. Simply add the 28 to both sides. We got that net force equation again from our free body diagram. The last part, part E, what happens if she's not exerting any force at all? So now your free body diagram looks like that. The block doesn't immediately stop. There's still friction acting on it, so there's still forces, but it doesn't come to an immediate stop. It's going to accelerate gradually over time. So since the sensor force goes away, now your net force is just negative 28 newtons. So plug in a Newton's second law, and you would get something like negative 8 meters per second squared. Again, understand that just because she stops pulling doesn't mean there aren't any forces anymore. Friction's still acting on it, and it also doesn't mean that it just comes to an immediate stop. It's still going to keep moving forward, but it's going to slow down gradually. Let's look at an example of a circular motion type question. On page 10, question number 1, the situation where you have somebody swinging a bucket of water. It gives you the mass and it gives you the length of the stream, and it tells you that the bucket swings 2 revolutions per second. Part A is asking for the period and the frequency. It's important that we recognize what that 2 revolutions per second is telling us. That's telling us the frequency. Look at the unit. The unit will tell you what you're dealing with. If it's a time, it would have just been seconds. Because it's revolutions per second, that tells you it's the frequency. Find the period just by doing the inverse. 1 over 2 would be 0.5 seconds. So that's your period. Part B, finding the linear velocity, we're just going to do v equals 2 pi r over t. Your time is 0.5 seconds from part A. The radius is simply the length of the string, how long it is, which is 0.75 meters. And you should get something close to 9.42 meters per second when you do that. Part C, we're going to use that velocity to figure out the force of tension. So first thing we have to realize is that the tension is a centripetal force. It's making something turn. So in that case, we set that equal to mv squared over r. Mass times the centripetal acceleration, in other words. So your velocity is your answer to B, 9.42 meters per second. Radius is still 0.75 meters. So you get something like 10 newtons for the tension in the string. Part D, simply talking about the centrifugal effect. That means that the bucket just wants to keep on going the same direction it was moving before. We call that idea inertia. Part E, if the bucket's string is cut, it's just going to keep moving in a straight line at a constant velocity. Again, that's that inertia idea. So same basic idea as your answer to part D and E. Part F, your diagram should look something like this. Moving in a circle, I chose my circle to be going counterclockwise. You could have certainly done it the other direction. Remember, your velocity is tangent to the circle. So your velocity arrows are always going to point directly outward like that, perpendicular to the radius. If you made yours go counterclockwise, then you would just flip each of those velocity arrows. Regardless of what direction you chose the bucket to be swinging in, clockwise or counterclockwise, your acceleration is always inwards, and your force is always inwards. That's why we call it centripetal. Centripetal means towards the center. So let's look at a projectile question now. So on page 11, question number 2, you've got a cannon being launched from the top of a cliff that's 45 meters tall with an initial velocity of 57 meters. So what we need to remember is that that horizontal velocity, that 57 meters per second, that's our Vx, our initial horizontal velocity. That 45 meters, the height of the cliff, that's the Vy. And ultimately, it's going to ask me to figure out how far my projectile travels forward. So x is going to be my question mark. Questions A and B are just about the nature of a projectile. Your answer to A will be yes, it's free falling and it's moving forward. B, the x velocity is what's constant, and the reason why is your answer to C, the only force acting on it is the force of gravity. There's no forces going forwards or backwards, so there's nothing to change the horizontal velocity. So your free body diagram in C would just be gravity pulling it downward. Part D, diagram the velocities. You got your x velocity, which is constant, so those blue arrows are always pointing forward, and they're always the same size. Your acceleration is due to gravity, which is downward, which is why your y velocity changes. It starts out at 0 and then gets bigger and bigger and bigger as it falls. When you get to part E, it's asking you to figure out the time the cannonball is in the air. Remember, we draw our table of givens by breaking it up into x and y. On the y side, you know what your initial position is, make it 0. And you got your initial velocity, or excuse me, your final height, which is 45 meters. On the x side, we know the velocity is 57. That should be meters per second. And we also know that x is our question mark. The other things that we need to remember are the initial y velocity and the y acceleration, and then we also need to remember that the two things are tied together by time. So in part E, it wants me to figure out the time first. Since I've got more information in the y side, there's no question marks over there, I'm going to use the y side to figure out the time. And the equation that we use in the y direction is the y equals y0 plus v0t plus 1/2 at squared equation. Just put in y's instead of x's. Remember, they both mean position. So, solving this thing for time. You know that both of those things are 0, so you can go ahead and cross them out. So that reduces to y equals 1/2 at squared. Multiply both sides by 2. Get rid of the fraction. So you get 2y equals at squared. Then divide both sides by a. So you get 2y over a equals t squared, and you need to take the square root of both sides, get rid of the square. So when you substitute your numbers, you get 3 seconds for the time, meaning it's going to take 3 seconds for this thing to hit the ground. Notice that doesn't have any dependence on how fast it's moving forward. That 57 meters didn't have anything to do with, 57 meters per second didn't have anything to do with the time. That time goes on both sides because that's the only thing that ties the two axes of motion together. Do part F, since I know what the time is, and I know that the horizontal velocity is constant, I just have to multiply the horizontal velocity by the time, and that would give me 171 meters. Hopefully this tutorial has been helpful to you. Remember that all the answers are posted in the classroom and they're also online on the website. If you have other questions, please don't hesitate to come in and ask and get more help.